mod 12. Okay, and in this expression, notice, so is this, I think this is what I wanted to say. Let's try this out. So for example, say if k is like 14, dimension of m14 is the dimension of m8 plus 1, whoops. No, I said M14 has one dimension 1, so I'm messing something up here.
Should those be floors?
What?
Yes. Those should be floors or
Huh?
yeah.
I should have 4 here?
No, floors.
Floors.
Oh, floors. Yes, you see, I was raised in an era before the existence of this stuff. They just used the bracket. You know, back in the days of typewriters, Underwood, you had this, and then at some point I noticed that people started to get rid of this, and then you had the ceiling function, and anyway, I never got used to it. I just tried brackets. Okay, so it's like we're speaking a different language. You have to translate this into English. Wiggle your fingers. Anyway, yes, raised integer, floors, if you wish. And so I'll just say recursive here, since I seem to have messed up the formula. So we want to get a recursive formula connecting the dimensions. And so everything is going to start with this calculation. Show that there are no modular forms of negative weight. Okay? And so we're going to start there, and then we're going to show these are all one-dimensional spaces, and then go to this, and then we'll try to deal with the case beyond that. Right? So let's show that this is zero-dimensional. The dimension is 0. There's no examples. The only modular forms of negative weight are 0. So how are we going to do that? So here's the kind of the key idea, is that, so let's suppose I have a modular form, weight k. So we know we have this transformation law, a tau plus b over c tau plus d to the k. Now at the same time, the imaginary part function. Remember I mentioned the imaginary part function has, well, if you're in SL2Z, this is for matrices in SL2Z, determinant 1 at least. Okay, that's what we're looking at here. The imaginary part is the determinant, which is 1, times the imaginary part over the absolute value of c tau plus d all squared. So if you look at this and you look at it and say, hey, you know what? If I raise this to the power k over 2, here's a numerator, denominator, and I get the exponents to match. So let's raise this to the power k over 2. Let's raise this to the power k over 2. And then let's just change this to a k. And now see if I multiply them, oh darn, I don't get cancellation because I don't have absolute values here, and I do have them here. Fine, let's put absolute values. We'll take our holomorphic, nice complex valued function, and we'll destroy it by just taking its absolute value. And so then that becomes an absolute value, and that becomes an absolute value. And so now when you multiply them, what we see is that the function absolute value of f times the imaginary part to the power k over 2 is actually an invariant function for the whole group, for all A, B, C, D in SL2Z. So this function, not f, not absolute f, but absolute f times the imaginary part, is SL2Z invariant, which means if you want to study this function and think about the values it could have, they all will arise somewhere in that fundamental domain for SL2Z. Because if the function is SL2Z invariant, every point can be transported in the upper half plane into the fundamental domain for SL2Z. So if you want to like prove a function is 0 or something, we can just study it on the fundamental domain. Now that I've gotten the idea of multiplying by the imaginary part factor to make it an invariant function for SL2Z. So we're going to study this funny product. I should say, by the way, it's almost true that you can go backwards. That if you have a holomorphic function, f, so that its absolute value times the imaginary part to this power is SL2Z invariant, it's essentially almost true that the function transforms like a weight k modular form. You have to introduce maybe some absolute value 1 character things in front sometimes, but it's almost possible to go backwards, which at first seems shocking because taking the absolute value destroys so much of an analyticity, but such is life. So let's take this expression and think about how it behaves on the fundamental domain. Okay? So the all the values of this function arise on the fundamental domain. Does that make sense? Because it's SL2Z invariant, the meaning of the fundamental domain, every point can be transported here by SL2Z, so the value of this thing here is equal to the value of this thing here. So we can just focus on things in there. For example, if I wanted to prove this function is 0, I can prove this product is 0. Or study things in here. So what can I do with this? Well, so this expression, it's not complex analytic, but this is certainly continuous. Continuous on the upper half plane, let alone fundamental domain. How does it behave when the imaginary part is large? So as the imaginary part gets big, as tau goes to I infinity, well, we know that this part is bounded. In fact, it has an actual limit. F is a modular form. And what happens to this expression? Remember, k is negative. It goes to 0. And this is the very first time we've used the negativity of k. All this algebra over here with the invariance, this just worked for all integers k. Positive, perhaps. Okay, and it's actually useful for other purposes. But here, finally, for the first time, I've used it. This is negative to put this together, and so we see then is that this function will go to 0. Okay, bounded times something goes to 0 goes to 0. So I have a continuous function on this infinite region, and as you go to infinity, it's getting very small. So I could just draw across the region at some height, I don't really care whatever the height is. You know, I can mark off a height above which perhaps the function has size less than equal to 1, let's say. Right? So up here, the size of this function we're paying attention to says less than equal to 1. And at some point it's going to kick in. Now, in this region here, we have the boundary across, down, around, the inside. This is a compact set. Continuous function, compact set, bounded. Real value continuous function in compact set is bounded. And so it's bounded here, it's at most 1 here, so it's bounded on the whole thing. And so what we get is we get that this expression is actually bounded on here. Now, since it's SL2Z invariant, it's actually bounded on the whole upper half plane. And now let's write out tau x plus iy. Okay. So this function is invariant in the upper half plane. Okay. How is that going to help? Well, I want to erase that. There's some space over here. So what is my goal? My goal is to show that the space is 0 if k is negative. Now here, let me write it like this: f of x plus iy is also equal to c over y to the k over 2. Okay. So how are we going to take advantage of this? So this is now true in the whole upper half plane. We use the fundamental domain. The fact that it was away from the boundary, let us say, this is compact. You see, if you had the fundamental domain and these points were actually on the edges, it would be very much more delicate. It's not part of it because it's not the boundary. It's not part of the upper half plane. Anyway, so we have this nice compact region to give that argument here. So this is on all of the upper half plane. So I'm going to now bring in the Q expansions. Okay, so we'll set our modular form has a Q expansion, an e to the 2 pi I n tau, and I want to extract the coefficient. So the way to extract the coefficient, since you're multiplying by an exponential, is to use the orthogonality relations between complex exponentials. So what we're going to do is we're going to consider, for an integer at least 0, I'm going to integrate from 0 to 1 f of x plus iy. So I'm going to fix a positive number y, right? Well, fix it, but I'm not going to tell you what it is, because later we're going to make it move. But anyway, fix the y, and now I'm going to integrate this against e to the minus 2 pi I m x. So the y is fixed, so it's like I'm at a certain height, and I'm integrating across from x equals 0 to x equals. I'm just integrating across a horizontal line segments of width 1. And the point is that this is integral of a sum 2 pi I n x e to the minus 2 pi I m x. And so if you put on your physicist hat, or you are a physicist, you don't need a hat, then you just swap the sum of the integral, integrate and pull out the constant an, integrate 0 to 1, e to the 2 pi I n minus mx. And this is awesome because that's an integer. And integrate from 0 to 1, if this integer is 0, well, this is integrating 1, so it's just a 1. But if this integer is not 0, this cancels. It's the orthogonality relation. And so what you're left with is the only term that survives, m is the thing that's fixed, n is varying. The only thing that survives is when n is m. Okay? And so I made a mistake because a modular form is not e to the 2 pi I n x. It's e to the 2 pi I n x plus iy. So I left out a critical term here. I left out e to the minus 2 pi I n y, e to the 2 pi I n x, e to the minus 2 pi I n x dx. But this thing has nothing to do with the x. So when I pulled out the integral, a n e to the minus 2 pi n y times the integral, and everything dies except for the term where n is equal to m, and so that's what we get when n is equal to m. So all that survives is that number. And so here's a number, and this is equal to, I'll just remind by putting it up here, okay, so here's horrible there. So by integrating this against that, I've pulled out a formula, almost a formula for the nth coefficient times an exponential factor for every single number m. Fixed to y bigger than 0, there's a formula for this term as an integral, and now I'm going to use that bound. The magnitude of this thing, that's a positive number, it's a complex number, it's at most the integral of the magnitude of this function. And this has size 1, so it doesn't even matter. You take the absolute value. Absolute value of that equal absolute value of that, less than equal to the integral of the absolute value. But this is less than or equal to c over y to the k halves, which has nothing to do with the x, and so you're left with c over y to the k halves. And so then you bring everything over, and you see for every m, I've gotten a bound on the mth Fourier coefficient. For each height y, I get this bound. It's like a function of y. And I want to kind of now start letting y vary to get some information out about the m. And again, this calculation, well, I guess it all did come from k being negative. Because, you know, and so, what am I going to do with this now? Now what I'm going to do is let y go to 0. Whoosh. From above, let y go to 0. What happens? The numerator just goes to 1. C times 1, c. But what's happening down here? You've got a tiny number in this denominator. Oh, okay. Small number downstairs raised to a negative power. So it's like, pretend y is 1 over a million. 1 over a million to negative power. So that's a million to a... Too many negative things going on here. What's happening?
Okay, the absolute negative, the absolute value of itself.
Yeah, so let's write 1 over y to the k halves. Oh, that didn't help. So if it's y to the absolute value of k halves. Yeah. Wait, is that right? 1 over y? 1 over y?
And it has to be the negative.
Y. Yeah, because I had a y to the... Yeah, that makes sense, right? Yes. Yes. So, we're all math majors, right? And so, as y goes to 0, what we see is that the bound goes to 0, and so that's 0, and so for all m, and so therefore, f is 0. Okay? We again needed a k was negative, yeah, so we can mess up some algebra. And so this proves that all the Fourier coefficients of a negative weight modular form for SL2Z are 0, and so therefore the modular form is 0. Series expansion is 0. So we use the Q expansion to prove that the function is 0. So now we're basically out of time, and so we've achieved the awesome result of showing there are no modular forms of negative weight, which is not really very interesting, but it's the first step. And so let me just show you an example of how we can use this to get dimensions of other spaces. So here's the key fact that we'll start with next time and then finally finish this proof. So the key fact is that there's a modular form, which is usually called delta, of weight 12, so that it's not 0 anywhere on the upper half plane. I don't think it's not the 0 function. I mean, it's a non-zero function. It never vanishes in the upper half plane, and its Q expansion starts off with no constant term. Starts off with a Q. So who cares? So what? Well, watch this. Suppose you gave me a modular form of weight 4. Okay? Well, then it has a constant term. Call it A0. If you take the modular form of weight 4 and subtract its constant term times the normalized Eisenstein series of weight 4, this is the modular form of weight 4. Now, if you divide this sucker by delta, because delta never vanishes on the upper half plane, this is still holomorphic on the upper half plane, but this satisfies the transformation law for weight 4, this satisfies the transformation law for weight 12, so the ratio satisfies the transformation law for weight -8. And, but wait, you have to be careful. Why is it in there? You have to check behavior at infinity. At infinity, the Q expansion, this vanishes. That's how I rigged it, so the constant terms cancel. Delta starts with a simple 0. And so in the denominator, you have a simple 0 at 0. And in the numerator, you have some 0 of order 1 or 2 or 3. And so the ratio is nice at infinity in tau or at 0 in q. And if delta had a double 0, this had a simple 0, you'd be screwed. But this has a simple 0. So anything that vanishes divided by delta is still OK and holomorphic around q equals 0 or tau equals infinity. And so this is really into space. And so that's the 0 space. And so therefore, f is equal to a0 e4. And that proves that the modular forms of weight 4 are just the scalar multiples of e4. And that just illustrates how in the low values of k, you can read off these things by pushing things into the negative weight space that you already know is 0. All right? So we'll wrap up this proof at the start of next time and talk about this very important example of modular form of weight 12. And then we'll want to say some things about L functions of modular forms and the Hecke operators. Okay? So we'll see those next.